guys, this is Dan from Maracana, and I'm going to be talking to you today about monads in the Scala language. Now, a monad is a concept that's probably going to be relatively unfamiliar to most folks that come from a procedural or an object-oriented programming background. But it shouldn't be too scary a term. It's essentially a kind of a design pattern. And design patterns is something that we use all the time in object-oriented programming, let's say. So, for example, your adapter pattern or composite pattern or strategy pattern or what have you. You can think of what I'm about to introduce here as sort of the monad design pattern, and it's something that ends up being used fairly commonly in functional programming and Scala in particular. So we're going to start with an example here. The motivation basically is to try to declutter this code. So what do we got? On the left-hand side, we've got three classes: foo, bar, and baz. So from foo you can get a bar, from bar you can get a baz, and from baz you can compute some value. We don't really care what the computation does. Just the idea is that you want to be able to, given a foo, get its bar, get the baz from that, and then compute. But the monkey wrench that we're going to throw into the works here is that any of these methods, get bar or get baz, could potentially return null. And in fact, let's say the foo that you start with could also be null. So on the right-hand side, you see sort of the typical strategy for coping with the possibility of null, or possibility of failed computations, or failed intermediate computations, is you check for null. So you say if foo equals null, then let's break out early and return null. Otherwise, we keep going. If the bar that we get from foo.getBar is null, then again, we break out early, and so on. And at the end of the day, we're able to return the value that baz computed. The other thing that you notice, of course, is that our compute method here returns a capital I integer object rather than an unboxed int, because again, we're representing the possibility of failure in this computation. So this is fairly cluttered code here. It's a pattern people are familiar with, so you sort of come to expect it. But you really have to squint a little bit to picture that the intent really is to say foo.getBar.getBaz.compute, and not have to worry so much about all the null checks. Okay, so another possible style that you might see to try to deal with the possibility of null, instead of doing the early returns to break out, this is even more verbose, although a little bit more sort of functional looking, is using these nested ifs. So instead of saying if foo equals null, return early, let's just say, well, if foo is not equal to null, then we'll proceed into our logic. And so the innermost part of our logic is we're returning the value of baz.compute. But then of course we break out into the series of else's where we have to return null each time again. So it's essentially equivalent code, and we really don't like that all that much either. So in Scala, using basically the same sort of a Java style, you can see if I flip back and forth here, these look basically identical. And really, we're just as unhappy with that. This is a pure functional technique here. There's no immutable or there's no mutable state. There's no early returns, but it's still ugly. It's still hard to read. So what we're going to do now is try to introduce the concept of a monad to deal with the sort of conflated concerns in that code. All right. So what's a monad? A monad is basically something that has this shape here, and notice that there isn't actually a trait monad in the Scala standard or standard libraries that you can inherit from. It's just if you want to write something that has this monadic design pattern, it's going to have this following shape. And the idea of a monad basically is to provide, like I say here, a standard interface for composing or sequencing operations on some value that's contained in the monad. So let's say that this monad contains some value A, some value of type A. Then the monad provides a method map, and keep in mind this is functional programming, so this is going to be a higher order method here because it's taking a function as an argument. The function is going to be able to, like we say, map from some value of type A to a new value of type B. What that'll give us is a monad containing our new value of type B. flatMap is a little bit more oddly named, and a little bit later on you'll see why it's called that. But essentially, it's fairly similar. We've got our contained value a, and we're going to take a function, again, higher order method here. We're going to take a function that translates a's into already wrapped monads of type B, and then return some monad of type B. So we're going to call that a monadic function that's being passed in the flatMap. So in particular, to deal with this sort of code bloat that we saw in our initial example, we're going to introduce the option monad. The idea of the option monad is to basically encapsulate the idea of possible failure in a type, rather than just saying, okay, well, this thing could be null or not null. So the two possible concrete classes that implement this option trait are called sum and none. So you can see sum has some value a, and none has nothing special. And what we want to try to do is define appropriate map and flatMap for both of these cases. So here's how this is going to look. Option is of the shape that we want. What we had seen before was we were going to have a monad of some type A, provide a map and a flatMap, each of which have the shape where map is taking a regular function, and flatMap is taking a monadic function, and both return a new monad, in this case option. So we want to actually implement these in our two case classes. So sum has the following implementation. Map basically takes a function f, applies it to the value a, and then wraps that up in a new sum. And flatMap, the implementation is even simpler. We don't have to wrap anything up. We've got our value a, and the monadic function gives us an option of b. So we'll just apply that directly. Now, for the next case, our none case, it's a little bit more interesting. It's very straightforward, but it's kind of cute. If we have a none value, in other words, a value representing essentially null or a failed computation, when we apply some function to that via map, what we would expect to happen is we still have null. We still have a failed computation. We're not going to pull a successful value out of thin air, right? And similarly with flatMap, even if the flatMap, or even if the function provided is, again, somehow able to pull successful option of b's out of thin air, still we have no a. We have no value for a, so we're just going to return none. And you'll see in a second how this has some interesting consequences. One point I wanted to just throw in here is that the standard Scala option class is implemented slightly differently, but at the end of the day, the way that they work is going to be the same. So going back to our initial example here, where we want to compute now, instead of an integer, capital I integer that could be potentially null, let's instead say that we're going to explicitly represent the possibility of failure with this option, let's say wrapper. So the possibility that our foo.bar could return, could not have a bar to return, we're going to say, okay, this is going to return an option of bar, which basically says, well, maybe we'll get one, or maybe not. Similar with bar's baz. And then baz, its definition of compute, again, that's just going to return a straight int. The computation, let's say, will always be successful. And what we want to do is define our new compute that's taking maybe a foo, or maybe nothing, and return maybe an integer, or maybe nothing. So let's break this down. Let's sort of start from the inside out. Let's say that we've got a baz, and we want to compute an integer. So that one's going to be pretty straightforward. This compute baz is going to have type int, and is just going to call baz.compute. So that's pretty easy. Now for the next step, let's say we're given a bar, and we want to compute the result from that, and we'll use our previous definition here of compute baz. Well, that's going to have type option of int because it could fail, and again, to define things in terms of our options map and flatMap, what we can see is that bar.baz could potentially fail, and compute baz, since that's a function that goes from, you remember we were talking in terms of monads that transform from some type A to some type B. Well, here we're transforming from some type baz to some type int. That's the shape of compute baz. So we can say bar.baz.map compute baz. Now let's try to fill in the next blank. We want to do compute foo, and again, this is going to probably return an option event. Again, it's the possibility of failure. And how do we fill this in? Well, the tool that we just developed was a method that takes a bar and an option event, and that's, you recognize that from our definition before. That's a monadic function. It's returning not just a straight int, it's returning an option of int. So what we'll do here is say foo.bar, which gives us an option, and call flatMap on that with compute bar. And then finally, we can define our compute overall similarly, saying, we'll take our maybe foo and flatMap compute foo on that, because compute foo, again, is a monadic function or monadic method. Now this is highly verbose here and probably looks a lot worse than it looked when we were just returning null. So let's collapse this a little bit. And this is starting to look a little bit more interesting. It's definitely much more condensed, and it's also nice in the sense that we don't have multiple points from which we can return from this method. Either return a value or return null. But this is fairly hard to read, so we're going to take a look at a couple more examples and then come back to this one. Example 2 here is, let's say instead of returning null from our get bar and get baz, let's say if we get a value back out, let's say that value is always real, but if for some reason we don't have a bar in foo or we don't have a baz in bar, let's say that can throw an exception. And also, just to throw an additional kind of twist into things, let's say that compute can also throw an exception. So the easy way to do this, if we were in Java, is to literally say, foo.getBar.getBaz.compute, and just accept that well, if any of these throw an exception, we're just going to propagate this out and just declare that our compute method will throw an exception. And that's all well and good, but it's a little bit sloppy engineering style in terms of well, you probably want to be a bit more informative about what kind of exception it was and where it came from, what caused it, perhaps. So let's expand on this just a little bit to give ourselves a bit more of an engineering challenge and say that if foo get bar throws something, we're going to actually throw something specific, a get bar exception. And similarly with bar, if get baz fails, we're going to throw a get baz exception, and if compute fails, we're going to throw a compute exception. So now things are starting to look a fair amount uglier. We've got some try catches, and we could split this up a bunch of different ways, but here's one possible way. We have one try block. Again, of course, this could be nested try blocks where we try foo.getBar and then try bar.getBaz and so on. But the point, of course, is that as we try to not lose any information about the failure that happened, we have to do some work. We have to wrap up our bar exception in a compute exception, wrap up the baz exception in a compute exception, and so on. And in fact, I still cut some corners here because I'm still not catching the compute exception to do something with that. I'm just letting that flow directly out from compute. So this is still fairly sloppy, and even so, it's clumsy. So I'm going to introduce a new monad that's similar to the option monad. We're going to call this one validation. This is going to be somewhat drinking from the fire hose here, so you may want to pause the video at this point and kind of scratch your head over this just a little bit. But I'll walk you through it pretty quick. This is going to be very similar to option in the sense that there's a trait that we define, and there are two cases. One case representing success, and another case representing failure. In this case, we're defining map and flatMap fairly similarly, and I'm going to not talk about lift fail for a second. That's a third method I've provided in here, but just hold that thought. Map and flatMap on the success case actually looks very similar to what it looked like in the sum case of the option monad. That is, when we call map and provided a normal function from a's to b's, we're going to apply that function to the contained value, our contained a, and wrap that f of a up in a new success object. If we call flatMap, that's going to literally just apply f using this monadic function f to a. And if that succeeds, it succeeds. If it fails, it fails. Our failure case is going to be different from none in the option monad in the sense that our failure case actually has some information associated with it. It has a map method, it has a flatMap method that that don't just return none. They return a new failure containing some E, and I'm using E to represent exception, but this could actually be any type whatsoever. It doesn't have to be something that represents a throwable or an exception or what have you. Now, to get back to this lift fail thing, this is something I should mention. I've based this validation monad implementation here loosely on the validation trait and case classes from the Scala Z library, which is very handy. I'm not going to talk too much about here, but really does a good job of filling in the blanks in the Scala standard library implementation. It's something that you should definitely consider using, or at least exploring for your projects. So lift fail is something I've borrowed, like I say, loosely from Scala Z, and what it's going to do is say, well, let's say we have a validation instance of type validation of E and A. So it parameterized on some error type and some value type, and we want to be able to use that. Essentially translate that into a validation of the same value type but a different error type, some validation of F and A. Now, just to point out, this is not something that is part of any sort of standard monad interface, but it's something that we're going to need because we're going to need to translate from our get baz exception and get bar exceptions into compute exceptions so that we can treat these all as the same type. So under success, our implementation of lift fail does nothing very interesting because we don't have a failure that we're dealing with. But in the failure case, where we're not containing a success value, we're containing some error value, then we need to essentially treat that sort of the same thing as map, where we create a new failure and apply some function f that translates from our error type E to a new error type F to the contained error value, and we'll wrap that up in a new failure object. So you'll see how I use this in a second. The way that we apply validation monad to our throwing exceptions example is like this. We do the same kind of thing where we say, well, we're going to flatMap on our possibility of failure from calling foo.bar, and we're going to flatMap again on our possibility of failure from calling bar.baz. And incidentally, this is the last thing I was just talking about, we're going to make sure that if there are any exceptions of type bar exception or type baz exception or what have you, we're going to lift that failure into a new compute exception. Okay, so cool, and this is definitely more compact and more succinct than we had before with our try catches, but it's still pretty hard to read. So our final example of the day. Oh, and I should mention that it's a little bit weird. In option, we saw basically flatMap on the outside, flatMap in the middle, and then map on the inside. And here we don't see any map at all. We just see two flatMaps. So this is a little bit different, and it's a consequence of my having introduced compute as returning a validation of something, an int, rather than just a straight int. So we'll see how to make this consistent with that pattern again in just a moment. All right, so our final example of the day, we're going to look at it starting in Java first again, is this idea of nondeterminism. And this is a little bit weird to think about, but think about a list as representing not a sequence of values, but rather a choice of values. So let's say, if our foo.getBars returns a list of bars, that it's actually returning a set of choices of bars that we could potentially choose from. So it's some sort of a non-deterministic choice, similar with bar.getBazes and baz.computeAll. And the way this ends up looking is going to be something that's, again, probably very familiar to a Java developer that's ever written nested loops. Is you loop for all the foo possibilities out of foos, and then all the bar possibilities out of get bars, and so on. And the thing that's a little bit curious here is at the top of the function we've instantiated an empty array list to contain our result set. And as we go through our set of nested loops, what we do is add all of our baz.computealls to that set of aggregated results, and then finally return at the end. So if you just ignore the fact that we're dealing with a mutable array list here, which in functional programming is somewhat taboo, it's really not too bad. And in Scala, it's even somewhat simpler, because that set of nested for loops turns into one for-comprehension, we call it. And so it looks pretty flat here, the way that we're saying. We take a foo out of our set of foos, we take a bar out of our set of bars, and a baz out of our set of bazes. And our results is yielded by baz.compute_all. And then what we do is, for all of that, we just yield our big fat set of results. Okay, so that's kind of cool. This is very readable. It's even simpler than the Java example, which wasn't too bad to begin with. So now the question, of course, is, well, what does this have to do with monads? We don't see any map or flatMap in here. And I didn't say, okay, well, we're going to solve a problem with the list monad. But, surprise, the for-comprehensions are actually a monadic construct. So I'm going to show you what that means here, and just define what these for-comprehensions are somewhat formally. So let's say I've got some pattern for, and then in brackets we've got a pattern that's being matched, or a variable that's being bound, if you want to think about it that way, coming from some expression, some initial expression. So for bar comes from foo.getBars, for example. Then we're going to yield e, so some new expression pertaining probably to the pattern. What that actually translates to under the covers, this is really just syntactic sugar for our call to map. So the assumption here is that this value e0, or this expression e0, is of some type that has a method map on it. The anonymous function that's passed to it is a function that takes this p0, this variable that's bound, and yields our expression e. So that's kind of interesting. And then similarly, if we have a for-comprehension that's a whole list of generators, pattern 0 coming from expression 0, pattern 1 coming from expression 1, and so on, the way that we translate that is, well, let's just break this down into expression 0.flatMap, pass that a closure or an anonymous function, taking our p0, and then define the rest recursively in terms of a new for-comprehension on the rest of what was there. So you can see that that pattern 1 yielding e1 and so on, and the only thing that we've broken out from that is expression 0 and pattern 0. Okay, so for-comprehensions, the way that we've defined monads, based entirely on flatMap and map, we can see the for-comprehensions operate on any kind of monad. So let's get back to this last example that we were looking at, where we did a for-comprehension over a bunch of lists. Let's now start thinking about this as, oh, it's the list monad. So let's go through our translation process based on our formalization before. Let's say for foo comes from foos. Well, what does that turn into? Well, there's a bunch of generators here, so this is going to turn into a flatMap. So the foos that were given as the function argument here, we're going to call flatMap on that, and pass that a closure that takes some foo and gives us another nested for-comprehension here. The way that we're going to translate that is, well, we're going to pick the bar coming from foo.bars off, and we're going to turn that into another flatMap. Then we look at baz coming from bar.bazes. That's going to be another flatMap. And then finally, we've got a for-comprehension on the very inside that has only one generator, so that's going to turn into a map. So that's kind of cool, and we can actually simplify this a little bit because this innermost map is actually just mapping on the identity function. So we can just toss that out entirely. So that's kind of interesting. We've seen patterns like this now. We've seen these series of nested flat maps and maps. So what if we were to take what we've seen here and sort of go in the opposite direction, taking our first two examples that had these nested constructs and turning them into for-comprehensions? All right, so our first example, based on the option monad, we had a maybe foo, and we flat mapped on that. We got maybe a bar, flat mapped on that, and then finally we flat mapped on the baz, got baz.compute. So let's sort of fold this back up into a for-comprehension. So starting from the inside out, let's say map. All right, so we know that's going to be some for-comprehension with one generator. This flat map is going to now be a for-comprehension with two generators. And the outermost flat map is going to be another for-comprehension with three generators. So that was pretty cool. We'll see that again in just a second. So we went from this case where we've got this whole nested series of if else's returning null at each step. which really conflates the concerns of doing your actual computation, foo.getBar.getBaz.compute, with the fact that we have to deal with this possibility of failure. And we've really slimmed it down into this very fairly slick little bit of code where we say, well, let's get a foo, let's get a bar, let's get a baz, and compute that. And the fact that we're coping with this, the fact that these are optional, that we could, return none instead of some int, is really doing a good job at separating concerns. The option monad is encapsulating that coping mechanism. We can do the same thing with our validation monad example. We can take these flat maps, and I also promised that we were going to make this more consistent with the option example that we had seen previously. Remember how I mentioned just a minute ago that if we're mapping the identity function, we don't have to include that in a map? Well, let's, just for the sake of it, throw it back in. So now this looks like the pattern that we're used to. We can say, okay, well, this map is a for-comprehension with one generator, and so on, until we get this series of generators all in one for-comprehension. And the fact that foo.bar and foo.baz are giving us different error cases, they're giving us a get bar exception and a get baz exception. The fact that we have to convert those into compute exceptions, it doesn't take a whole lot of typing here. We just say, well, we're going to lift that into the particular monad type that we care about here, which is a validation of compute exception and int. And so you can see this looks very similar to what we saw before. So I'm going to close out here with a bit of a roundup and summarize by saying basically that a monad is a pattern that captures policies for function application and composition, meaning the policy in the case of option was to propagate failure. The policy in the case of the list monad was to basically do the equivalent of nested for loops, do the Cartesian product of all of the lists combined. So that's the policy, and we basically hide that or wrap that up inside our map and flatMap. And then as sort of syntactic sugar that helps us make this look really pretty, for-comprehensions provide this sequential looking syntax, and it's all done on top of map and flatMap. So we're gonna see this pattern fairly frequently. Some monad making something explicit in the type system while hiding something else. So in the option case, we're making the possibility of failure or the possibility of missing data explicit by saying, oh, we have an option of int, while hiding all of the boilerplate if non-null logic. That's very convenient. Similarly with validation from Scala Z, we make the possibility of errors explicit, and the errors, of course, have some type and some value, but we hide the boilerplate try-catch logic. We also saw the list monad, which makes this possibility of nondeterminism, or the possibility of having to deal with a bunch of different combinations explicit in the type system. And we hide all this boilerplate of nested for loops. But there's other monads that we haven't gotten a chance to look at here, and I'd encourage everybody to play around with these as sort of an exercise for the reader. There's some really great kind of wacky monads out there that end up helping encapsulate other concerns. So the state monad and sort of an extension, a logical extension on that, the undo monad, make the presence of mutable state in an algorithm. The idea that for each sequential function call, you might actually get a different result given the same arguments, just because there's some state that's being modified in the background. It's making that possibility explicit in the type system again by saying, oh, we've got a state of something, or an undo of something, while hiding the fact that we have to propagate those state changes through our algorithm recursively or whatever. There's another monad called promise, which is really cool. It's similar in a sense to the option monad, and even simpler in a sense because, well, I'll just say what it is here. It's similar to the idea of promises from Java util concurrent or what have you. The idea that we're doing some asynchronous computation and we get a promise of some future result. We don't know when we're going to get it. But let's, assuming that we do get it at some point, we're going to sequence those computations. Let's say we have a bunch of these monadic asynchronous computations, and we want to make that possibility, or make the fact that they are asynchronous explicit in the type system, but not have to worry about all of the threading logic, all of the joining on a thread to wait for its completion, and so on. The transaction monad is another interesting one. There's a number of different implementations of it that you can find across the web. It makes the notion that a computation could possibly be rolled back after being completed. So some state that was mutated could be undone in a transaction. It makes that explicit in the type system, again, while hiding the fact that we actually have to do these rollbacks at some point or another. And the list just goes on from there. So hopefully you've seen that using monads, at least in our simple examples here, are a really nice way to clean up your code, to hide the fact that you have to do some repetitive logic that doesn't have all that much to do with the actual computation you're trying to affect. You really kind of want to sweep that under the rug in some sense. Make it explicit just in one place without having to repeat yourself. And that one place, of course, is in the type signature. So the option of int, for example, and leave all the rest out. And like I say here, I want to encourage everybody to use monads wherever you can to try to keep those concerns separate, to try to avoid that conflation of concerns and keep your code clean. So thanks again for listening, and hope you enjoy classes from Americana.